First of all, I'd like to thank Professor Makowski for having invited me in the ISR too. It's a great pleasure to be here after many years. The last time I was here was in 1986, so that's gives you an idea. And what I'm going to try to talk today about are really issues related with respect to non-convexity and how they impact, in some sense, our ability to perform distributed resource allocation in networks. And I will talk about two issues really, both in the wireline and the wireless context, because in some sense, although the problem is the same, the solution implementation is slightly different and therefore leads to different sort of mathematical issues. So what is it? Yes, okay. So the motivation really in communications is network is, again, the standard spiel that I can give. There's, of course, you have scarce resources, but it turns out, of course, we need to do resource allocation, because when you have diverse quality of service requirements and you have dynamics of time varying environments, then this basic issue of providing diverse QoS really gives rise to these non-convexity issues. And the non-convexity issues, I will talk about a bit how they really come about. And so, this is, of course, the question of when you want to allocate resources. The question is to try to find a common framework in which one can do it. And the way we approach this whole problem is kind of a utility and pricing based framework, but it just is a kind of a jargon that is being used, but I'll show you why it really comes about. So what do we mean by utility? A utility, of course, in both a wireless or a wireline framework is what is the satisfaction obtained by the user for what they're asking for, okay? And so we try to quantify it, and what we claim is the users requiring different quality of service have slightly different utility functions, and so that means these different quality of service requirements can be mapped onto different utility functions. And what we think of price really as the cost of the resource, of how much the resource you're going to allocate. And really the whole idea of control algorithms in networks is really to allocate resources in such a way such that the user operates at a level of satisfying some sort of utility requirements, and at the same time you want to maximize, achieve some system goal, and that is also going to be reflected. And the reason that there is this notion of dynamic pricing is because depending on the state of the environment, in some sense the prices for the very resources that you're going to allocate is going to be different, okay? So this is just the general setup. And so we can give a very basic formulation that if UI is the utility function of a user, and X is the amount of resource that you allocate to it, in some sense bandwidth, the problem is very simply stated. It's the maximizations of the sums of utilities, so this is some sort of a system utility, subject to some capacity constraints. And what are the capacity constraints is, well, that every link has some amount of capacity, and the amount of capacity that you allocate to a particular set of users on the link. So Aij is just the incidence matrix, and Aij is equal to 1 if user I uses resource j, and so it's a very general formulation, okay? And X is the amount of resource that is allocated. Here we can think, either we think of power, we can think of bandwidth. So power in the wireless context and bandwidth in the case of a wireline network. And although you can even map bandwidth through, if you can think of log of 1 plus signal to noise ratio, this is the capacity of a wireless channel, so you can also map it in terms of bits, and you can put these capacity constraints, okay? So this is the general setting. So it's a very general formulation, and these are general utility functions. And now this is where the issues coming. If all utility functions are concave functions, then we have very nice theory of convex optimization where the necessary conditions are given by the Karush-Kuhn-Tucker conditions. And we can then use duality to get a very nice distributed implementation. So in some sense, for me, this notion of primal dual ideas from optimization theory is not so much that but it actually has very great implications in terms of implementations. And I'll come back to that a little later on. So in general, of course, utility functions can have this type of behavior, a kind of a sigmoidal, a concave or a sigmoidal behavior and a convex behavior. And I will argue that the moment you put these QoS constraints, you really have to operate with utility functions of that type. And of course, so what are the issues that really, what are the difficulties that imposes? So some ideas. So for example, traditional data services in the internet have concave utility functions. Sigmoidal-like functions are associated with either real-time services or many of the services in wireless networks, and convex functions are sometimes also associated. We can have some services on wireless networks. And of course, in general, you cannot formulate these as convex programming problems, although you can do the following. You can convexify the problem by many ways. One, look at the convex hull. Two, you can do, the other approach is do what is called, and I'll come back to that a little later on, what is called the augmented Lagrangian approach. You sort of add a sufficiently powerful convex or concave function as an addition, which disappears at the optimal point, and so that the overall function is nicely concave. But you cannot quite do that if you want to get nice distributed implementations. And so the question is, what can we really do? So I'll just give you a very naive approach. Naive approach, suppose you have 11 users, you have a resource capacity of 10, utility function is kind of a threshold function, which is, it's just a step function that if x is greater than 1, utility is 1, if x is less than 1, utility function is 0, so it's really a step function, which is the sort of idealization of your S type of function. So we know very simply that if we allocate 1 unit of bandwidth to 10 users, then you get a total system utility of 10, and 0 to 1 user, then you got a 10 system utility. While if you take approximation of this function by a linear approximation of x for x less than 1 and 1 for x greater than 1, so a saturation function, then the optimal allocation here is to give each user 10 by 11 and then obtain a modified utility of 10 by 11, but an actual utility of 0 for the entire system. So clearly, what it tells you that the moment you have non-convexity, if you're interested in bringing about system utility, you have to do something. In this case, what it says is basically you have to choose 10 out of the 11 users if you want to get, you want to maximize system optimality. But the question is, how do you choose them? Okay. So what we have been doing is trying to address these problems for non-concave utility functions, and the goal is to find a good approximation for optimal resource allocation with a simple and a distributed algorithm, because you want to implement it as a distributed protocol on a network. Okay? And I will talk today about this downlink power and rate allocation problem in CDMA networks and rate control in an internet type situation. And I'll show you that the solution concepts are slightly different because the implementations are different because of what is the level of centralized information that can be available, centralized control that is possible. Okay, so let me talk about power and rate allocation. And we know in CDMA networks and in general wireless networks, power is the most important resource, and the allocation is really the trade-off between the performance of each mobile. In the in what is called the uplink problem, we know this power management, what we really try to do is we try to do a power management by which everybody balances their power roughly to get the same signal to noise or inference ratio, or signal to noise ratio at the base station. And the power control is done this way, sort of equalize that. So to equalize the near far effect. So somebody very far away broadcasts at very high power and so on and so forth. But you try to balance this in such a way that there's just enough destructive interference to equalize the SNR. And all these power control mechanisms in quite common devices just operate based on this. It is in the classical sort of cellular telephone context. So but in addition, in wireless networks, in the data thing, you have variable data rate, which you can get by variable spreading gain. And there's a trade-off between the data rate and the probability of transmission success. And therefore, the two resources we want to really optimize in wireless networks are both optimizing the power and the data rate allocation. Okay, clearly, the higher the power, the higher the data rate that you can send, and so on. So there's some relationship. So let me talk about some related work. This was this work of Sayadar and also Xiao and my colleague Nashraf and so on. So really, you formulate an uplink power control problem as a non-cooperative endgame, and really you can show that they'll basically look at the uplink problem and really show that if everybody tries to sort of do this power control type of power allocation, then you can achieve a Nash equilibrium. And we know Nash equilibria in general are not Pareto solutions and Pareto inefficient, and so in a network in which you have this ability to do some sort of centralized thing, particularly in the down, where you have this notion of a base station, you want to try to achieve a Pareto point. So you want to do slightly better. So then there was this recent work of Marbach and Berry, where they looked at sort of revenue and total system utility maximization for the downlink with concave utility function. And they used the sort of classical, Karush-Kuntaka conditions, and just came up with this. And then there was this O and Wasserman paper, which really looked at the uplink problem, and so looked at power and processing gain problem, and they looked at a single class where everybody is the same, and the only constraint was not on the total system power. They didn't put any constraint on processing gain, but they just put a maximum power constraint on each user, and she really showed that really the optimal solution is kind of bang solution. So either they operate at 0 power or maximum power. Okay, and then there was this work of Baedeker and also Berggren, who looked at the joint power and rate control in the downlink CDMA without constraint on maximum data rate. And so this is the paper by Berggren. This is the people from AT&T, Lucent, Borst, and all these people. So they really showed that the pure TDMA is optimal. So what I will show you in the sequel is that by formulating this problem and looking at the two things, you will see many situations where we put constraints on the power, we put constraints on the data rate, what are the impacts, what are the and you can get some nice insights on when TDMA is optimal, when pure CDMA is optimal. Okay. So let's look at the problem if you want. We have downlink power and rate allocation for CDMA networks. So we consider a single cell with a total power constraint PT. Each mobile I has a variable data rate with a maximum data rate, which I call R max I, or a fixed data rate, so it can allow both. And then let Fi be the probability of packet transmission success. So, and the goal is a power and rate allocation. So you want to allocate these two quantities, what rate they should operate and what power they should be allocated, which maximizes the expected total throughput of the system. Any questions? Please feel free to interrupt me, okay? Because I keep on interrupting people. So, so the signal to interference ratio for mobile I, we know we can write it in terms of suppose the total of m mobiles in the cell. Then you have the gain path from base station to mobile I. This is the interference due to all the other mobiles, and this is the background interference at an intercell interference for mobile I. And we call AI the ratio of the interference power to the gain of mobile. So notice here GI is outside the summation because GI is just related between the mobile and it is again associated with mobile I. Okay, so this is so W is known as the chip rate, RI is the data rate for mobile I. So now, as you can see, the typical, depending on the type of whether you binary phase shift key and all the type of modulation schemes that you have, you get different sort of probability of success as a function of power. And you see that all of these functions have this kind of non-convex behavior. Okay, and so the question is where you want to operate. Basically saying that if your power is too low, this is just, you're not just efficiently using the resources, so your probability of success becomes low, and in a low part. So there's a threshold after which sort of the channel becomes useful. Okay, so the properties are really, it's a concave function of its own power. So it can be either in a region where it is convex or concave. Okay, and so we can formulate the problem as the following. Yeah.
So in the previous slides, if you just had S function, that includes the other two cases, right?
Yeah.
I mean, so there's no need to say concave.
No, you don't need to. Yeah. But what I'm just trying to say is that really there are two parts of this function. One is the concave part and one is the convex part of the function. And it's a question of which part to and then the idea is really want to operate the system when everyone is in its concave part of the function. Okay. So the idea is that, so therefore you can write the optimization problem very easily here. So this is the rate times the probability of success subject to the power constraint. So this is the average throughput. So sum of the total average throughput of the system subject to the total power constraint. We also know that each one of these mobiles has individual power constraints. They could be smaller than PT, but let's just make PT for, they have their own rate constraints, or you could have mobiles which operate at fixed rate. Okay, so this is a very general formulation of the problem. So to maximize, it's very simple to see that you want to allocate these powers. So Pj is the power allocated out of this total power Pt by the base station to mobile J. Okay, so so one of the things we know is that the sum of the Pj's must be equal to Pt. It's obviously best because that will improve the utility. So that's one thing which comes. So in some sense, to maximize total expected throughput, the base station must transmit at maximum power limit. So if it has power available, it must allocate it. That's one of the first things you will see. It is very trivial to see. And therefore, you can rewrite the SIR formula in just as a function of Pi. That means this gamma I, so the utility function for user I only depends on its rate and its power, because the total power must be allocated. That's a one simplification that you get immediately. And therefore for a total, and then also we know that if we have an allocation Pi, then the optimal rate to maximize, so keep Pi fixed and look at the maximum over Ri, then you immediately get this solution. That Ri star, the optimal rate must be this. If Pi is less than this quantity, you can allocate Ri max if Pi exceeds this quantity, and if it just operates, if it is a mobile which cannot change its power allocation, then its Ri star is the allocation anyway it was given. Okay, so these are the sort of rate allocation as a function of power. Whereas gamma I star you can find, yes?
How do you find this rate allocation?
Just, let's go back. You have these constraints here. I mean, you have this function here, right? So keep Pi is fixed. So you assume that all these constraints are satisfied, right? And now, just with respect to these constraints, optimize this function. So fix P. So assume the power, you've got an allocation which satisfies your power constraints, and then just look at a optimization over R, and this is just direct. Okay. So now, having done this, what it really says is that the entire system really is just a function of the powers. It's not really an independent problem of rate and power. But the moment you do this, you see that all the utility functions are now either of this form, either convex, concave, or an S function of Pi. Okay? Depending on which region it is. So, what do we do? Well, let's define the Lagrangian, and we're going to look at the dual. So you want to hit the total power constraint, and therefore what we want is let P bar lambda be the power as a function for a fixed lambda which maximizes this. Okay? And so what we really do is the following. Let's look at each mobile. We define Pi lambda as the max of the, since we know its utility function is just going to be a function of Pi which is allocated to it. So look at, it's the largest P for a fixed, for every lambda, which makes this, which keeps this positive. So this is what we call, this is in some sense a power allocation, and we're going to look at what is going to be its maximum willingness to pay. Okay? And then we're going to, so for each lambda, we're going to define Pi lambda to be this. And at the base station, our aim is to allocate all of this PT, so we want to minimize the difference between PT and what we allocate to all the mobiles, subject to the total power constraint. And the idea is, of course, base station adjusts this price lambda dynamically to obtain a good approximation of this. So how the question is how to really do this. So the question is, of course, P lambda can be discontinuous. There may be no equilibrium allocation, and so we divide really the problem two stages. There's no equilibrium allocation in some sense, and that's usually the case when you cannot allocate all of those guys to be in the good region of their utility functions. Okay. And that happens because of the non-convex, I'm using convexity in general, but non-convexity of the functions. So that means what, if you look at the Lagrangian, it's like the dual. So the dual becomes non-differentiable and so on. So, and that leads to this discontinuity. So really we divide two stages. We do what is called the mobile selection stage. The mobiles are us that are allocated power are first selected. So we try to do a procedure by which we select, like the first example to say that we have to only select 10 out of 11. So we try to select those guys who are going to be in the useful part. Of course, now we're in a heterogeneous context where everyone has different utility functions. There's not the same utility function. So different path gains and so on and so forth. So we first decide which to select, and then we do the power allocation to the selected mobiles, and that turns out to be a standard convex optimization problem, as we will see. So we define the maximum willingness to pay as, remember, we define P lambda as the largest quantity, power, and we call lambda I max as the argmin with respect to lambda such that this quantity is 0. Okay? So in some sense, lambda I max is the maximum minimum price to pay, such as the net, if you can think of this as the net utility minus lambda, what is the price it's going to pay, times the power it's allocated. So, and this is the net utility. So lambda is the largest value where the net utility becomes 0. So let's do the mobile selection stage, and suppose for the M mobiles we can order the lambdas in decreasing manner like this. And then we select mobiles from 1 to k are selected where k is such that if I select the corresponding lambda j max and plug it into that pi function, the allocated powers will meet the total power constraint. Okay? So the question is, the first theorem is, of course, is that this selection algorithm provides an optimal selection problem for E, and so now comes the power allocation stage. Is suppose once these are selected, then we can solve and find the equilibrium price such that that constraint is met. And it turns out that this, once you do this sub-selection and these prices with respect to lambda star, you can actually show that the power allocation, because you only selected k out of m, this is actually a Pareto optimal point for the system. You can actually prove that. Okay, so I won't bother. Now the question is, how good is it? How much of a price are you going to pay over the actual theoretically possible maximum utility that you could have obtained for the system? Well, what you can show that really you will be not worse than the worst utility, this is quite obvious, of any one of the mobiles. But on the other hand, if all the guys are small enough, so you have a large number of users and nobody requires that much power, which will be exactly PT, right? So if there exist many mobiles requiring small amount of power, so their own mobile, their power constraints are not really PT but smaller than PT, then in fact you can show that the error becomes smaller and smaller. And basically you converge asymptotically to the global solution that you get. So you get a large system effect. Okay? And so now let us look at what sort of insights you can get. So this gives you some insights on the transmission strategy. So now we've got this ordering of these lambdas, suppose. Okay, we've got this, we've ordered the mobiles according to the lambdas. It turns out that if you compute P1, which is the guy with the largest willingness to pay, but evaluated at the second highest willingness to pay, of the second highest willingness to pay, if this exceeds PT, then we know pure TDMA is optimal, because there's nobody else you can serve in that time slot. So you only select the best guy at that. So that means you select one user at a time in each time slot. That's going to be the optimal strategy. If this is true for all M, that is T, that is you take the willingness to pay of the worst guy in the system and you evaluate PI at that, and the sum, if that sum meets your capacity, your power constraints, then we know all of them can transmit in that environment, and therefore CDMA is the pure optimal strategy in that environment. Okay? So this is just very simple corollaries that you get. On the other hand, if you have Ri being, remember we had this Ri max, which we had computed for each for a given power allocation. If Ri max replacing the Pi by PT, or if there is no rate constraint on all the mobiles, then again TDMA is a pure optimal strategy. So TDMA is precisely Qualcomm's HDR. So in each slot, you take the guy in the best environment, give him the maximum power, and shoot out all the thing to him. This is really the whole thing. So what it says is that, of course, therefore, pure TDMA of transmission is optimized only for high data rate services or system with high interference. Okay, and in general, static transmission strategy could be inefficient, and therefore we need dynamic strategies, because this is at time slot per time slot. So this is sort of the. Then, the other corollaries you immediately get is in terms of mobile selection strategies, and these are quite obvious that if you have two mobiles with the same probability of success of bits and the same sort of gains, then clearly if Ri max is greater than Rj max, you will select I over j. And if they have the same maximum transmission rates, but one has a better success probability, then you will select that, and so on. So basically, if you have a single class of mobiles, the mobiles in a better transmission environment have a higher priority to be selected than mobiles in the worst transmission environment. And multiple class, there's no general rule, but it all depends on sort of this real sort of configuration of parameters that they really have. So so you look at some examples. If you have a probability of success given by such a quantity as a function of the SIR, and then you have a path gain with a distance function of the drop-off in the, and you compare it with HDR, where HDR is each base station transmit at its maximum power limit and transmit to only one mobile at a time. So in HDR transmit to the best mobile. So you compare with that strategy, then you can see the rate allocated, and this is how often class 1 and class 2 are selected. This is the actual throughputs that you can get, and this is the throughputs that you can get with HDR. Okay.
Somebody from outside the area, what does HDR stand for?
High data rate. This is Qualcomm standard. This is how Qualcomm does it in the current system. So you can see there are substantial things, and obviously, as we see, if the maximum rate at which mobiles can transmit have no bound, then they're going to approach the same limits with HDR. That's what the theory told. So if mobiles have rate limits, then HDR is not an optimal strategy. Then these are for other parameters with respect to B is this parameter of the gains. So again, we'll see what happens if Bi is less than Bj. Then we know the probability of success of I is greater than the probability of success of J. And again, what is the impact of that? Again, you can see the difference between looking at things more carefully and taking a very naive approach that HDR takes. And then this is what's the right way to say it? Again, one being in the convex region and one set of mobiles being in the concave region. Again, the effect. So you see here, mobiles B2 don't get selected at all here.
Excuse me.
Yeah.
What's the difference between class 1 and class 2?
That's what I didn't. We have this utility function, right? So class 1, in some sense, what is going to happen is let us see. Both have, in the sense, it just depends on the utility function, which part of the utility function they are most likely to be in, whether they have a concave type structure or concave or convex type structure. That's really the. And so what we see is that by doing something smarter, by looking at this sort of real non-convex structure, you can really improve a lot and get some insights into the whole resource allocation strategy in wireless networks. And currently we're looking at some problems. For example, I'll tell you where we're going. We're looking at the uplink problem, and looking at the uplink problem again when you have different utility functions and what happens. And there, in the uplink problem, again, because again we have a base station, you can begin to look at a centralized solution, and there is a slightly different solution concept that can be used as over this.
Talking back to the slide that you had before.
Yeah.
The one where I see the zeros and zeros there.
Yeah.
So that means that it's totally unfair.
It's totally unfair. So you have to impose fairness.
So clearly, what that says is that Qualcomm living out of the revenues of customers, is certainly not going to use this, right?
Yes. No. I mean, yeah. See, the moment you select, what is the selection strategy saying? That by selecting these guys, you are really paying a big penalty to your system. Okay. Obviously, this is not a good solution, because you have to introduce fairness. Hopefully, but this is a very static environment, right? So from time to time, your whole channel conditions will change and things will improve. But really, yeah, what the pure problem tells you is that this is not the solution to the whole problem, right? So in fact, what we have done in our more recent work, and what I will tell you, is we have combined this with actual scheduling. And the scheduling is to include this notion of fairness, because when you realize that such situations can take place, it's not obviously very good that you don't select class 2 mobiles, right, by this procedure. So in fact, so in that problem, in fact, when you do the scheduling, it's really opportunistic scheduling, and in some sense, in that problem formulation, the randomness becomes very apparent in the problem formulation. You cannot look at the static sort of environment that we're doing.
How many users do you have in this environment?
I have to go back and see. I don't know the exact numbers, but I don't know here. No, yeah, then.
Comparable to what the HDR system would support?
Yeah, I would guess so. Yeah, I mean this is like of the order of hundreds of thousands, that type of thing. Okay. I don't know. I will have to go back to the paper, but I don't have the figure exactly, the number. So let's come to the second problem in the remaining time that I have. We talk about rate control in the internet, and the problem is slightly different. And the reason is the following: that the solution concept, the problem formulation, in some sense is the same. Of course, you don't have the signal to interference ratio playing an important role, but the reason the situation is very different now is that in the mobile and base station sort of context, you had a centralized object like a base station that could begin to select, to either select, or in the uplink case, you could do some centralized computation. Okay, so you have this centralized body that can actually select. In the internet context, where you have these users trying to just access a certain amount of bandwidth, you don't have this ability to do the selection anymore. So now the question is, how can you try to get the users to select the allocations, bandwidth allocations, which will in some sense do the same optimization problem without the centralized ability to select the good guys in the good region? Okay, so this is the whole idea. So again, the related works in all of this. We know, of course, the work of Kelly, the law of Lapsley, and then this is work of myself and Heikel and Rosenberg, and this is a work of Kunir and Shrikant, which is really implementing these types of solutions using random loss and ECN marking. Then this is, of course, work that has come out of here. This is the work of Richard. Assumptions are such: you have these convex utility functions. They are essentially convex optimization problems, and they're very good for elastic services, traditional data services, and so on. So the moment you want to bring in again QoS stuff, you can. It's very easy to see that I do not know whether he has put I put this calculation over here, that even if you take a standard MM1Q, try to maximize throughput subject to a delay constraint, and you look at the utility function now, it becomes a non-convex function. Okay, so let's take this simple example. You have routers, you have a capacity C, and you have a number of users, sources, and destinations. And user hires utility function UI. It's an increasing function of data rate allocation, but it's concave or a S-type function, and each user has a maximum data rate MI. The question is, how would you implement the same solution? And so the problem formulation is exactly the same as before, except that we cannot use the algorithm for power allocation since there is no central controller to select users. Okay? So this is really a question of looking at the same problem but finding a different type of distributed algorithm to do it. So again, let's look at the dual problem, define the Lagrangian, and the dual problem is minimize Q subject to lambda greater than 0. And even though the utility functions are non-convex, we know that the dual function is always convex. The only slight catch, it's convex but not differentiable. Okay? So again, define xi lambda the same way, define the maximum willingness to pay, and then you can show that really you have your discontinuity at these points. Yeah. Yeah, this is also a general dual gap. Yeah. But in this case, you can show that there is no there is no duality gap, but you have this discontinuity. In general, yes, there is. Now, so if you look this is of course some ideas even tried out by I think Carr and Leandros, right? They tried out this sort of subgradient algorithm. So the question is, okay, let's look at the subgradient, and we know what a subgradient is. So subgradient is just it would be the gradient if it were continuous at that point. Otherwise, because convexity is just given by this definition. So this D is just the subgradient out there, and it turns out that subgradient in this is precisely C minus the sum of all the band users who use that link. So this has a very interesting implementation. In the implementation of in the context of a network, the problem is transferred from the number of users to the number of nodes, and at a node you only have to carry the information of the throughput of the users who use that node, so you don't need any other information from outside anywhere else to compute the subgradient. Okay, so that's the advantage of implementation. Okay, so it has a very natural interpretation in terms of implementing something. And then what you can do is you can do a subgradient projection algorithm to really update, to try to find the lambdas, which are your Lagrange multipliers or prices at the link. And these are really your congestion costs. But the key is, of course, you get this very natural decomposition. So this is in the number of variables. So J, which is the number of links, is usually or J is the number of nodes, much smaller than the number of users. So this is a much smaller problem, and more, it's got completely from the information of the users who use that link, and not any other user. So you can have all that, and the total aggregate rate is the only thing that is usually available at any router, because they cannot keep the detailed state information of the individual rates of all the users, but they can keep track of the aggregate rates. So this is also an additional sort of important consideration to keep in mind in regular sort of routers that you get, how much information that you can get.
There's no additional condition on, for example, the sum of the squares of the alpha n beta gamma?
Yes, in fact it should be there. Because it's a stochastic approximation type algorithm, right? But this is, I think this is enough. This is a deterministic case, so you don't have the additional thing to do. Okay? So, how do you do the distributed algorithm implementation? Each user determines its transmission rate by looking at, for each lambda n, the maximum rate at which you can transmit to keep this, to maximize its net utility. Okay? And the node problem is, of course, solve this. And through this iterative procedure, you try to converge. And it turns out that if you look, what is the relation to the primal solution? If there exists a lambda star such that this is equal to 0 exactly, so that means you can achieve this maximization, then you can show that the allocated rates that you compute based upon these lambda n actually converge to the optimal primal solution. Otherwise, in general, this does not converge at all. And in our context, it does not converge if there exists a user k0 such that this is its utility function is an S function. So if you have a convex optimization, purely convex optimization problem, it will work very well. But the moment you have non-convexity, you're out of luck. Okay? And what happens in this case, the primal solution oscillates between feasible and infeasible solutions, creating congestion in the node. So clearly, you cannot just implement this algorithm blindly. Okay? And so we have to meet some sort of self-regulatory property, because in the original problem what was happening, you see, what happened was when you had these utility functions, S-type utility functions, the mobile station did, what it did was it selected those guys such that everybody was in the concave region, and you never ran into this problem because the rest of the problem implementation became a pure convex optimization problem. Now, of course, you have this problem. So the question is, how can one do it? Well, what we define it is that you sort of have to do something ad hoc now. That user does not transmit at maximum data rate even though its price is less than the maximum willingness to pay, if it realizes it will receive net utility by transmitting data. That means, so a user looks at, computes its net utility function. If for the particular allocation lambda hat n, its net utility comes out to be negative, and you have to do it for how long? For a couple of iterations, then you say that, well, it decides to just drop out of the system. So you have to have a mechanism. You can implement this as a protocol. You cannot implement this on human beings, because human beings will anyway try to get through. Okay, because knowing that, you know, at the next iteration your lambda might improve and allow you to transmit, so you just transmit anyway. Okay, so what is it? Each user has a threshold such that if it is non-positive net utility, including negative utility for THI iterations consecutively, it does not transmit data anymore. So this is in some sense. So what you have to do is you have to modify the following. For a given lambda, it's x lambda if this is less than this, and this is some function, some continuous function, if for that particular value of lambda, it's sort of becoming infeasible, where x is some function such that you know, these conditions are verified, and a good candidate for such a function is a function which is this normalization, so sharing of the capacity. So if you choose such a function, then you can show that really, I'm going to skip all of this, is there exists a constant step size alpha for which the proposed algorithm converges. And the second thing which is very interesting, I think, is you have this asymptotic optimality. As again, if you have a large number of users in a system with large capacity, and the set of users who are being in that strange set, you know, where these things don't happen, is relatively small, then in fact you converge to one. Relatively small says that as the number of users goes to infinity, the size of that set, which I have, you know, go back, I think, yeah, do we define the set S K naught? No. Well, yeah, this is a set, I don't know whether we define it, I think, yeah, this is the set. Okay, where it is defined. So it's just it's some of these users who are taken, who are in the bad part where they will oscillate. If that turns out to be finite, as the number go to infinity, then in fact this goes to 1.
Is the conversion very fast?
It depends on alpha, the step size. And typically for these algorithms, if you look at the network, in fact, it's not very good. If you really look at it, the convergence, this alpha has to be smaller than the inverse of the Lipschitz constant of the system, right? It's a dynamic system, so Lipschitz constant can be large, and so you have to find a way to alternate your alpha. And of course, the worst case scenario for such an algorithm is if all the users have the same utility function. Then you will find that all of the users will stop transmitting data at the same time. And therefore, the possible solutions, of course, is randomize the utility function of each user, and therefore each user has a lambda I max with some high probability, or you just randomize threshold of tolerance. Don't keep the threshold of tolerance the same. And then you will get again convergence. And the complexity is about the same. The only additional thing is this quantity that you have. And what you need to do to implement this algorithm is you need to measure the received data rate by counting the number of ACK packets, or you can do it by explicit notification of the destination. And again, just to show you the numerical results, so you have different users with different types of utility functions, right? So user 3 and 4 have this stat function. User 1 and 2 have nice concave functions. This is what happened. So, without the self-regulatory property, what happens is that these guys operate, and here they start oscillating so much that the simple distributed algorithms, there's so much noise for these systems that things don't happen well. Whereas if you introduce the self-regulatory property, it turns out that there comes a point where user 1 just decides that the system is not good enough to provide the QoS that they want, and they just get out of the system, while the other guys start converging towards the allocations, optimal allocations.
What happens if, you say, there's a fixed alpha for which what about the system is large, and we don't know what alpha could be, right? So if you start with the wrong alpha, then what happens?
You will get a lot of oscillations, I think. You will get a lot of oscillations in these things, and you will have to sort of then the next best thing is try to just look for local convergence. Okay. And the same thing. Look at the received net utility of the users, and again you see something very interesting that happens. And so the summary is, of course, instability and conjecture in non-convex system. The basics of message I want to give you all, rather than just read out what is there on this slide, is to tell you that really non-convexity has important implications. And the moment you try to introduce QoS, or you want to do in wireless systems, you have to deal with the non-convexity, and therefore you have to think of solutions to deal with it. For example, there are very many elegant ways. As anybody who does any nonlinear optimization theory will know, you can do this augmented Lagrangian, convert everything to a nice concave function and try to use concave optimization methods. Question is, if you do that, in fact, you will see that the constant that you have, even if you can look at the dual and try to get the distributed implementation, is so large that this alpha becomes so small that your convergence becomes extremely slow. Or you get this non-separability of when you look at this dual, in which case you don't have this very natural decomposition to look at it from the point of view of links versus users. And the advantage of looking at this primal dual formulation, in my opinion, as someone who has worked in this thing approach, the idea that what optimization theory has really brought into all of these internet problems and all of this, all this work of Lowe and Kelly and all this stuff, is this primal dual theory has taught us two things. In fact, by the way, the primal dual theory was first done in a paper that we did in somewhere in 1990. Okay, but the idea of this primal dual theory is really that it and you know, this work of Masulia and Roberts to identify the kind of utility function that is used by TCP is that once we realize that all these class of algorithms are really nothing but primal dual algorithms at work, getting this structure allows us to perhaps define better protocols that we might try to implement in the internet for the network to achieve, in some sense, better operating points that we might desire. So that's the advantage of this whole approach, that by doing it in this manner, we don't do things ad hoc, and we can actually perhaps design things that are better. And of course, you know, Richard has also done much work on this, you know, generalized fairness and all of this stuff, and this ties in very much into this primal dual theory and how you will implement this. And the fact that we know that this theory allows us to get from, has a very natural interpretation in its dual formulation as being something which you can do at a link and only work with that link information, is this additional important insight that you get. Okay, and final thing is, you know, some of the insights that we got to really see when TDMA, when CDMA is optimal, and so on and so forth. This approach clearly throws that out and brings it to the forefront, rather than, you know, trying to really study and plot various curves and try to figure out which is better in which case. Okay, so I'll stop over here. Thank you.
Let's first. It's the only 48 slides, and there's a 49 that is there, so.
Yeah, I want to leave it.
Any questions, comments, please?
I have a question. In your paper, you define a parameter lambda, and then you order the lambda for given user, and you select who will transmit.
Yeah.
And then for these selected members, you do the optimization problem. Then because it is a downlink CDMA system, it's more kind of centralized system.
Right.
I want to say, is there any other direct way to do it? For example, I can measure the different users' channel gain.
Yes.
And then I order the channel gain, and then select the user with the largest channel gain, the best channel, and then try to allocate the resources.
Okay.
If anything left, I send something
Okay,
left.
that's fine. Except that would be true if everybody were having the same utility function. The channel gain would be a measure of the ordering of the lambdas, if that were true. In the heterogeneous case, you cannot get that. So therefore, you have to compute the lambdas. Okay, so you're right. Everything else being the same, then channel gain will define the lambdas. But if everybody has different utility functions, then the channel gain doesn't define the lambdas.
The lambda should be.
Then the right parameter is the lambda. Okay?
In your rate control algorithm, what happens if there's some misbehaved person because you suddenly everyone so nice backing off momentarily?
These algorithms really have to be implemented as protocols. So a given ISP might implement it as a protocol in the network, right? If you ask really every user to implement it, then there's this question of cheating and malicious users and all, then you cannot do anything. Okay? I mean, it was like at a recent NSF workshop said that the next greatest challenge is to design an internet which is robust against every fault that you do not know about. How the hell can you do it?
But this rate control has to be at the user.
So it has to be at the user level, but it is really by signing on to this ISP, you are agreeing to the rules of that ISP. I mean, so the protocol is really done by the ISP. It's not really you who are doing it. So that's the only way I can think of feasibly implementing such solutions. You know, otherwise, if it's left to the user, I mean, we already know, you know, right now you just go and play with your TCP stack and set everything, and you can do things that are not really permissible, right?
Any other questions? Comments? Jokes? Complaints? No. So let's thank the speaker again. But before we do this, let me remind you that he will be with us until 5, 6 this afternoon. He can be seen in the flesh after 2:30 in the library of the Center for Hybrid and Satellite Communication. And I understand that
If you are all interested, I don't know how many of you are interested, I'm willing to give a second talk on sensor networks, on energy issues and how stochastic geometry can be used to solve a very cute problem. It's not very profound, but it's cute. That's all.
With this as an added appeal, if you wish to meet him or talk to him after 2:30, you know where to find him, and I understand there's a process of the second floor and of the 49th slide.
49th slide. Actually, you want to see what the 49th slide is?
Thank you very much.
Good to see you. Good to see you. Interesting thought.
Maybe just